Hello students, in this video I am going to talk about flip-flops. The starting flip-flop is SR flip-flop and D flip-flop. So first of all, let us discuss what is the difference between a latch and a flip-flop. In the previous video I have discussed regarding the latch. The difference between latch and flip-flop is clock signal. In latches there are no clock signals, whereas in flip-flop the output is only going to change with the incoming clock signal. And what is a clock signal? Clock signal is nothing but a continuous trail of zeros and ones. So let us start. First of all, just a small discussion on the topic NAND gate, because I am going to use the truth table and the output of NAND gate again in the cases of flip-flop. So let us start. I have taken a 2-input NAND gate over here. A, B, 2 inputs we have, Y is the output. So the conclusion is minimum 1 input is 0. In the case of NAND gate, output is going to be equal to 1. So this is the truth table of NAND gate as discussed in latches as well. The conclusion that we are going to use for the discussion of flip-flop. So this is the SR latch using NAND gate, which I have already explained in the previous video that how it is going to work. So S is the below signal, R is the above signal. So for 0 0 we have invalid, 0 1 we have 0 1, that is known as reset condition, 1 0 we have 1 0, that is set condition, and 1 1 we have no change condition. So students, I will just using the output from the SR latch directly in the conclusion of SR flip-flop, and we will try to calculate that how SR flip-flops are working. So now here comes SR flip-flop. So the difference between SR latch and SR flip-flop is we are going to use a clock signal over here. As you can see, CLK stands for clock signal, which is a continuous trail of zeros and ones. So it is going to have the constant amplitude, students. It's a continuous trail of zeros and ones. So gate number 1, gate number 2 are the two input NAND gates we have, where input is S, input is R, and the another input is clock, which is common to gate number 1 and gate number 2 both. Gate number 3 and gate number 4 is nothing but our SR latch. The same circuit diagram which I have just shown it to you. So this dotted portion which I have shown over here is nothing but SR latch. And in SR latch, as you can see it over here, in SR latch we have the below signal as S and the above signal is R. So if I am going to talk about SR latch, this is signal S and this is signal R. So let us start the discussion over the topic SR flip-flop, that is set reset flip-flop. So I have written an empty truth table over here where I have mentioned clock, S, R, Q and Q bar. Q and Q bar are the outputs, S and R are the input signals which I have mentioned over here, and clock is this signal, the input signal which we have used. Again, gate number 3 and 4 are representing our SR latch, and in SR latch the below signal is S and the above signal is R. So students, let us start. The first case I have taken when clock is 0. So I have written over here cross. Cross means don't care term. What does it mean? It means that it can have any value, 0 0, 0 1, 1 0, 1 1. It will not have any effect on the output. As you can see, when clock is 0, minimum 1 input 0, output is 1. Once again, minimum 1 input 0, output is 1. As you can see, there is no impact of the value of S and R. They can have any random value, but minimum 1 input 0, output must be equal to 1. Minimum 1 input 0, output must be equal to 1. Now S is 1, R is 1, and this is nothing but SR latch. And already discussed that when S is 1, R is 1, in SR latch using NAND gate, output is known as no change condition. So I am not going to repeat the whole process of the working of SR latch again. Just by using the previous outputs that we have already discussed, I have concluded the output to be equal to no change. But if you want to see the whole process once again, you can refer my previous video on the topic of latches. So case number 2, here comes our case number 2. So what is case number 2, students? Now I have started applying the clock signal, and then we will observe that how the outputs are changing. So when the clock is 1, now I will start providing the input signals S and R. So the first case is 0, 0. So let me show all the values over here. Clock 1, S0, R0. So let us start. Minimum 1 input 0, gate number 1, output 1. Minimum 1 input 0, output 1, gate number 2. So once again, when S is 1, R is 1 in SR latch. I repeat, when S is 1, R is 1 in SR latch. Output is again known as no change condition. So students, the next case number 2 condition also provided us the output to be equal to no change condition. So here comes our case number 3. So now what is case number 3? When clock is 1, S is 0 and R is 1. So let us now start with this case number 3. 0, 1, the output of NAND gate, 0, 1, output is 1. 1, 1, the output of NAND gate is 0. So now students, this signal is S and this signal is R in SR latch. So in SR latch, when S is equal to 0, R is equal to 1. I repeat, for 0, 1 in SR latch, output is 0, 1. Hence, I have got the answer 0, 1. Again, I am not calculating the whole latch process again. I am just using the previous topics, the previous concepts, the output of truth table as it is for SR flip-flop, because SR latch is the basic building block in all the flip-flops that we will be using. So that is for S0, R1, output is 0, 1. For 0, 1, output is 0, 1. That means reset is high and the output is reset, and this condition is known as reset condition. So here comes our case number 4. Now what is case number 4? When clock is 1, S is 1 and R is 0. So 1, 1, output is 0. 1, 0, output is 1. Once again students, this is S and this is R signal. Now for 1, 0, I repeat, S is equal to 1, R is equal to 0. For 1, 0, output is 1, 0. So this condition is known as set condition. So you can see it over here, 1, 0. What is set condition? So when set is high, the output Q becomes set. Set means 1, reset means 0. So again, I have utilized the previous truth table from the SR latch for just getting the output of SR flip-flop again. The last case, case number 5, when clock is 1, S is 1 and R is 1. So 1, 1, output is 0. Once again, 1, 1. Sorry. 1, 1, output is 0. So this is your signal S and this is your signal R. So for 0, 1, 0, 0, output is invalid. I repeat students, when S is equal to 0, R is equal to 0. In SR latch using NAND gate, output is known as invalid. So this is the whole truth table that we are going to have in the case of SR flip-flop. Repeating the whole truth table again, when clock is 0, doesn't matter what is the value of S and R, output is no change. Now when we start providing the clock signal, here our SR flip-flop will start working. The first case is 0, 0, no change, 0, 1, 0, 1, 1, 0, 1, 0 and 1, 1, invalid. So this is the truth table of SR flip-flop using NAND gate. Now the next flip-flop which I am going to now discuss is D flip-flop. D stands for delay flip-flop, and students, D flip-flop is nothing but a special case of SR flip-flop. As you can see, I have already designed an SR flip-flop over here already. And what is D flip-flop? I have connected signal S with signal R through NOT gate. I repeat, I have connected signal S with signal R through NOT gate, and this will start behaving as D flip-flop, that is known as delay flip-flop. Now let us discuss the truth table of D flip-flop again, for which I will be utilizing the truth table of SR flip-flop. So let us start. So case number 1, I have clock input, I have D input. So I have written it over here, clock D. So students, when clock is 0, D, don't care term, can have any value, either 0 or 1, doesn't matter. But the condition is when clock is 0. So D can have any value, maybe 0, maybe 1, doesn't matter, that is don't care term. So just remind the previous case which I have discussed with you in SR flip-flop, that when clock is 0, doesn't matter what is the value of S and R, the output is going to be no change condition. So here as well we are getting no change condition when clock is 0. Next case, now we have started providing the clock signal. So now when clock is 1 and D is 0. So students, when D is 0, D is directly equal to S, so S will also become equal to 0. On the other hand, when D is 0, here we have a NOT gate, so R becomes equal to 1. For S is 0, R is 1. The truth table of SR flip-flop, which I have just discussed with you, for 0, 1, output is 0, 1. That is reset condition. And the last case, case number 3, clock is 1, D is also 1. So when D is 1, S will become equal to 1. On the other hand, through NOT gate, R becomes equal to 0. So for students, 1, 0 in SR flip-flop, 1, 0, output is 1, 0. So you can see I have just used the outcomes of the SR flip-flops over here for the implementation of D flip-flop. Now let us discuss the last and the most important point over here, why this is known as delay flip-flop. When clock is 0, in actual your flip-flop is not working because the previous condition will remain as it is. But when input, D input signal is 0, output is 0, D input is 1, output is 1. So that means my input is exactly same as my output signal. That means D is equal to Q. But a delay is going to be created over here. How the delay is going to be created over here? The delay of the working of all these gates, NAND gates, NOT gate, which we have connected over here, because as you know that all the gates are actually having the delay. When we provide the input signal, it will take some time, although the time is very small, but it will definitely take some time to give us the output. So combining all the delays together, although D will directly become equal to Q, but with a delay. That is why the D flip-flop is known as delay flip-flop, which is just generating the delay, but the input will become equal to the output signal. So this is known as D flip-flop. Thank you so much, students.